Good evening. Since no one has joined yet, we'll wait for a couple more minutes. Thank you.
ஃபாலோ பண்ற அதுதான் இன்னும் எப்படியோ ஒரு இதெல்லாம் நடந்துச்சு அப்படின்னாரு. என்ன நீங்க என்ன அதிசயமா பேசுறீங்க? உலகமே வந்து தப்புன்றது முக்கியமான ஒரு விஷயம் வந்து சொல்லுது. நீங்க என்னடானா இல்லைன்றீங்க அப்படின்னு. சரிம்மா, இப்ப என்ன
Dr. Ramasubbu, could you please mute yourself?
இருந்தோம்.
Good evening, everyone. So we are waiting for a couple of minutes to allow others to join. Good evening, everyone. We are just waiting for a couple of minutes to allow some more people to join. Thank you. Good evening, everyone, and welcome to week 3 of the live session for Fundamentals of Additive Manufacturing Technologies. I am Sourav Goswami, a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. My research area broadly is additive manufacturing. First of all, a very happy Independence Day to all of you, and good evening, and let's get started. So, our agenda for today would be for those of you who are joining for the first time, introductions. I have already introduced myself. If you feel the need, you may also introduce yourself, your motivation behind taking this course, and what are your expectations from the course and from the live sessions. Then we'll do a quick recapitulation of the lectures that were covered in this week, followed by a problem-solving session in the later half, where we'll try to get our concepts cleared, and hopefully the problem-solving session will help you in solving your own assignments. Once again, for seamless communication, please raise your hand, and when I call out your name, you may please unmute and speak. If I am not paying attention, you may kindly interrupt me. And otherwise, please remain muted at all times. Thank you. That will ensure that this session goes on smoothly. So, in the first lecture this week, we spoke about tool path planning. Uh, these are Professor Kapil's slides, and the various topics that were covered in this week included the area filling methods such as grid cutting, pixel mask, raster, and others. Uh, some topology optimized or continuous area filling methods, spiral mat contour, and we'll see. So the need for toolpath planning is actually to deposit materials in each layer. So currently we are aware that the starting point of any additive manufacturing process is a 3D CAD file. Then we tessellate it to obtain an approximate representation. The tessellated file is then sliced, and for each slice that we obtain, we program our AM machine to print it layer by layer. And it is during that printing of each slice that toolpath planning comes into a picture. So now I have a contour such as here. I know that it has certain exterior contours or external contours and internal contours. I know that maybe the material is to be deposited somewhere in these regions, whereas this won't have any material. Similarly, if this is my entire build plate, maybe these regions also won't have any material. But what is the optimum strategy to actually deposit material in this region? And by varying this deposition strategy, what other factors can I influence? For example, can I change the part density? Can I change the strength of the part? Or the accuracy with which I am capturing these outer contours and this inner contour? And these are the various aspects that we'll be talking about today. And as already mentioned, tool planning is a very critical step for computer-aided process planning for AM. Now, mainly when we talk about toolpath planning, we refer to the infill. That is, we focus our attention on the regions that are interior to the exterior contour. So we're talking about the bulk here, how to deposit material in this bulk. For the external contour itself, or the internal contour also for that matter, it is very easily done because when we have already sliced our STL file, we already have the contours. So once you have the contours, and as Professor Sajin Kapil also discussed in his lecture, you know what are the points of intersection of the facets with any plane. So what remains is to just interpolate between these points and you obtain your contour. Now, for an STL file, we know that the representation is approximate. And so even linear interpolation is sufficient for joining these dots. However, if you are in performing a direct slicing, which captures the geometry more accurately, then some other forms of interpolation might be needed. And for area filling, that is filling up the bulk or filling up the interior in each layer, it can be of two types. We could be aiming to fill a 2D surface or a 3D surface. And some of the most commonly used strategies are grid cutting, pixels, mask, and path. There are certain criteria which govern the efficiency or the suitability of any area filling method. So, four of them are listed here. Number one is quick heat dissipation. Now, we know that in any AM process, the powers involved and the power input involved can be pretty high. For example, in DED, uh, the laser heads can have power that go from say anywhere between 3 to 8 kilowatts, and this gives rise to a very high heat input. So that heat needs to be dissipated, and we know that it is the thermal gradients and the transfer of heat which actually governs the microstructure's evolution, the solidification characteristics of the finished part. As such, an optimum toolpath plan will allow for quick heat dissipation, or in certain cases controlled heat dissipation. Again, if heat dissipation is insufficient, the workpiece may heat up and warp due to thermal expansion. And we should ensure that such distortions from the design geometry are at a minimum. The second is to minimize the number of lifts. So what happens is, we know that for a process such as DAD or even FDM, where material is being extruded from a nozzle and the deposition head moves in the XY plane, it is at the start and stop of the printing process that most of the time is spent because of the inertia of motion involved. Thus, whenever the deposition head is to stop printing at a point, maybe shift position or even has to shift the Z height by the layer height, the time is not really useful. I mean, we are not devoting that time to printing. So it might be counted as time wasted. Thus, if we minimize the number of lifts, the total printing time or the total process time in this case would go down, and this would make the process more efficient as well as more economical. Also, during the start and stop of the material deposition, the process is said to be unstable. Why is that? It's because of the inertia involved. The amount of deposition at the start or stop, or even at the corners, may be more or less than the extrusion that we have designed it for. As such, there may be bulging, or so there may be bulging at certain points. So you have more and more material being deposited, or there might also be depression. And either of these is a variation, or either of this is actually a defect because it is moving away from our design geometry. Again, the machine feed rate should be constant to ensure uniform deposition, and the step over should be constant. And it is defined as the distance between two adjacent scanning tracks. Now, the first area filling method that we encounter is called grid cutting. So it is especially suitable to processes such as laminated object manufacturing. So remember that we spoke in one of the previous sessions how there can be two approaches to laminated object manufacturing. One is form, then bond, and the other is bond, then form. Now, in form then bond, first we are actually printing our shape in each layer, and say I have many of these corresponding to each layer, and then I join them together by any means, such as by ultrasonication or others. In the other case, when I am bonding and then forming, I first bond the sheets together. And finally, when they're bonded together, I perform the subtractive operation on all of them to obtain my final geometry. Now, so in certain processes, such as laminated object manufacturing, we need to remove all of this extra space. So if this is my shape, then all of this sheet is extra and unwanted. So I have to figure out a way to actually remove this extra material, excess material, and retain only my useful geometry. And this is where the grid cutting method comes into the picture. So we did not have nothing but just a Cartesian grid of in the XY plane. And the unique thing about this is that the grid is actually made on the regions which are unwanted. So this region is unwanted, as well as this interior contour is unwanted. And the region that is of use to me is not actually discretized or is not divided into this grid. Then this unwanted region, once it is divided, may be removed by any suitable means, such as by using a laser, or if your sheet material is weak enough like paper, then you may also use a knife. However, as you can see, because of the resolution of this XY grid, the resolution of your final printed part will also vary. So maybe when you cut, you have, I mean, depending on what tolerance you are having, it might either be positive or negative, but it will not capture the exact geometry. So you will have varying cusp height along the sections, and maybe your final printed geometry ends up looking something like this. Another area filling method, which is similar to the one before, similar to grid cutting, is the method of pixels. The only difference being that in this case, we are actually pixelating or concentrating our focus on the wanted region. And it is specially suited to certain methods such as digital light processing based VAT photopolymerization, binder jetting, or material jetting. And in these processes, the energy source or the light is shown directly on these wanted regions only. Again, as you can see in the figure on the right, the resolution of your final contour or the resolution of your final print will depend on the resolution or the size of these pixels. The finer pixels you have, the better resolution you can achieve. Another area filling method, which uses a floodlight, is actually a mask based method. So, somewhat similar to optical lithography. Here we generate a mask which is nothing but a negative of the pattern that we want. So, assuming that this is my desired output, this will be my mask where the black regions are actually opaque to the wavelength of the energy source and the white regions are transparent. However, one thing has to be kept in mind, which is that similar to optical lithography, the distance of this mask from the the final surface where we are actually projecting it must be controlled optimally so that the final shape that we achieve is similar to the mask, because it will be subjected to diffraction of light. And say diffraction at the interfaces, if this is my mask, so these are the opaque regions, and in the middle we have the transparent region. And when light interacts, so it is not necessary for the light to pass straight through. And there will be certain diffraction effects that come into the picture, and these may distort the shape. So this distortion must be controlled suitably. A very popular and commonly used strategy for filling an area is a raster scan. So in a raster scan, this is simply just a unidirectional or a linear filling pattern. So we start from one side, say in an X raster scanning, we start at one side, stop at the other. Then we lift our deposition head, we do stop depositing, and then the tool head travels back to the new start point, which is again in the same direction. So here, all the odd numbered points are start points, and all the even number points are actually end points. And between these red paths that we see are simply the tool travel without any deposition. A similar raster scanning methodology may be adopted in the y-axis, depending on which, I mean, in what direction of your printed part you want, what sort of properties. So it is expected that, say, for a y raster scanning, the tensile properties along the y direction itself may actually be better than those obtained in the x direction for this case. And of course, to homogenize these properties, we use what is called an XY raster scan, where we are scanning in both X and Y directions. Another, perhaps more efficient method of scanning is called a zigzag. So here, we minimize our deposition times by actually not switching off the tool deposition, and we do not waste any time in actually the travel of the tool head from one point to the next. So it is depositing continuously, and there are no intermittent stop points. So once it starts at point one, it will go to two and keep depositing, travel to three, four, five, six, and so on. There are no Normally there are no stop points in between, and it will end only when it is done scanning the entire surface. Now the disadvantage of this would be that the exterior contour would only be approximated by straight lines. However, by adjusting the step over size of this toolpath, even this error might be minimized, but it is still a valid consideration. This zigzag pattern, sometimes also called a bilinear pattern, is very commonly used, and it is a common method in AM. It consists of segments in both forward and backward motions, and also within the boundaries of the cross section and along the boundaries. Next, a nature-inspired area filling method, which is actually contour path, where once we have the contour of the desired shape, we simply keep offsetting it by a specified distance, which in this case would be the step over, such that each contour is actually similar to the outer boundary at the beginning. And as we progress inwards, the shape conforms more to this interior boundary. So as we'll see, the contour is actually evolving. So here at the outermost layers, it is pretty similar to this outer boundary in green. Whereas once it reaches close to the interior, it takes on a more polygonal shape. Thus, the contour is constantly evolving. While this gives very good density and very good printed characteristics, one common defect which can be easily guessed is that for certain complex shapes, it might leave voids, such as can be seen in the example to the right. So in all of these regions, we have these voids. And this is because after a point, the aspect ratio of these contours becomes so high that they basically degenerate and they do not deposit any material. So it is very good for regular shapes. However, for irregular or complex shapes, it might not be so suitable. A spiral path is very commonly used in numerical control machining. However, its application for additive manufacturing is pretty limited as of now. Again, there are certain cases such as a circular cross section where it might be very useful, but for the general case, it has very limited applications. The next set of methods are actually space filling paths, where we have these complex shapes or complex paths, such as a Hilbert curve, which is illustrated at the bottom, and others such as piano curves or E curve, etc. And these complex curves are actually used to fill the entire contour. It has certain examples, such as the step over everywhere is constant, and it has only one start and stop point. So even the lift up time is minimized. However, it is not suitable to all types of curves. It is only suitable to mostly rectangular or square curves. And for other complex geometries, we have to use suitable trimming operation. The next method is MAT. So MAT actually stands for medial axis transformation. And the origins of MAT are from biology. So I think initially this was called the skeleton, as it is similar to a skeleton. So we have a complex shape, and what we're actually trying to find is, say, the skeleton of this object, which is traced out here. And around the skeleton, if we give, say, if we imagine that the flesh and meat of a biological body is placed, then we'll end up with our shape. So, yeah, it had biological origins, and it is especially useful because traditional methods like contour cannot adequately cover the geometries of parts, especially when they are complex. We saw in the last slide how they may leave voids or gaps. And how this mat is actually calculated is that, so what we do is we construct circles, and we try to fit a circle of a suitable size such that these two edges of the external contour act as tangents to the circle, and we keep recording the center. So say at this time step, this is my circle and this is the center C1. At a later time step, the circle would have grown in size, and I recorded center again. Say this is C2. Again, at a later time, the circle would have grown larger still. Say this is C3. And once I perform this operation over the entire contour, say it will branch off here as well as here and progress throughout. And I collect all the centers. And they need not form a closed curve or even one single continuous curve. As we see, they have branched off. We join all these centers together and we obtain the skeleton or the medial axis. And once we have the medial axis, we deposit uh, by offsetting this medial axis, and we try to cover the entire contour. Also, as the slide says, it is known as a skeleton and helps describe the domain shape based on the medial axis. Bisect the domain to get the skeleton of the inner geometry. It is very useful for complex domains. So wherever the space filling path or the contour path fails, medial axis transformation really becomes handy. Of course, the most sensible thing to do would be to actually use a hybrid path which combines the best of both worlds. So depending on my region or the area of application, I can use a combination of paths. So in this case, as we see, the exterior boundary or the exterior contour has been filled using a contour path to maintain or to preserve the geometric accuracy. So we have maybe two layers here, so two to three layers, which is usually called the outer boundary or the perimeter. And then once we reach the bulk, we deposit in a zigzag path. So this will ensure that we get good density, a high infill percentage, as well as shorter process times as the number of liftoffs are minimized. And it is actually the hybrid path which is most commonly used in DD processes such as FDM or DED. So usually when your machine will start depositing, what it will do is say this is the final contour. So it will start with maybe 2 to 3 based on how many you define contours. And then it will switch to a raster, for example, for filling the interior. Also, there are certain upcoming methods such as a continuous path where we program or we plan our toolpath in such a way that it will, there's only one path, a very complex path, which fills the entire domain without any single lift off. So here, in on the example, in the example to the right, assume that this is the start point and this is the end. Now, in this particular example, the start and end points are close by. This need not be the case, but we see that the entire curve has only one start and one stop point, and there are no lift offs in between. So once the complexity of the pre-programming step is overcome, this toolpath deposition strategy may actually prove pretty helpful as it totally eliminates any lift offs. But again, finding such paths for every geometry or for a general geometry may not be as straightforward. Then again, there are area filling methods that are based totally on the topology optimization. And these are actually area filling methods in 3D because these will extend in the 3 dimensions. A very common example that we get is that of honeycomb. Honeycomb structures are very strong in compression. And there are certain others like gyroid. Gyroid is very commonly used in biomedical applications. And of course, we have the triangles, trihexagon, across 3D, and others. Swash also. Similarly, like we have to fill the area on a 2D surface, which is restricted to a plane. We may also have to fill the area of a free-form surface, which is actually a surface in 3D. And this is an up-and-coming area of research. And there are three main types of area filling methods which were discussed in the lecture: direction parallel, contour parallel, and space filling. So direction parallel may be thought of as something similar to the zigzag, but in 3D space, of course. So this need not be a plane. This surface can be curved in space. Contour parallel is again similar to contour filling or contour offset, and space filling is a new method where we fill the surface based on the geometry, the final geometry itself. So there is no predetermined strategy or no predetermined contour which we simply recreate or offset or any similarity between the contours. We keep going in 3D space based on the final geometry that we want. So I also have an example video of a space filling technique for something called direct writing, which we'll see in the upcoming hour. In the second lecture this week, we were introduced to liquid additive manufacturing. And some of the major topics that were covered in this week are okay, maybe this is not the correct slide. Okay. So, yeah, we were introduced to liquid AM. And among the 7 methods that are classified by ASTM, being wet photopolymerization, material jetting, binder jetting, material extrusion, sheet lamination, powder bed fusion, and directed energy deposition. Wet photopolymerization and material jetting may be classified as liquid-based AM process. Why is that? This is because in these cases, the build material and often the support material also is actually a liquid. So the starting material is in liquid form, the feedstock is liquid. And thus, these processes are referred to commonly as liquid additive manufacturing. One may argue that, uh, say, the binder in binder jetting is also liquid and it is jetted. So, should that also be classified as a liquid-based AM? The thing to note there is in binding binder jetting, our build material is actually powder, and it is actually the binder material that is liquid. So, as per ASTM, it cannot be classified into a liquid-based AM process. As we discussed, a liquid AM process uses a liquid in the form of raw material. That is, the build material and the support material should be liquid in nature. And as per Professor Kapil's classification also, so we have classification based on the type of raw stock. So the raw stock can be any of the states of matter. It can be liquid, solid, or gas. So for gas, there are no widespread or prevalent methods as such. As I shared in the first weekly session, there are certain nano additive manufacturing methods which utilize aerosols. So those are still particle based, but I mean we are getting close to maybe a gas based AM setup. It uses a very rarefied gas and a very low density of aerosol particles to manufacture intricate structures at the nanoscale. And among these liquid raw stock based AM methods, we may have photopolymer based, which is stereolithography, or rapid freezing, for example, water based. If our raw stock itself is solid, we may have a sheet based method such as laminated object manufacturing, or powder based methods such as SLS, selective laser sintering, DED, directed energy deposition, or 3D printing, as it is commonly called. Should we have a raw stock which is wire, we may have FDM or a wire arc additive manufacturing. We may also have DED, and we saw in the last session a couple of videos on wire-based DED. So let us discuss the working principle of photopolymerization-based liquid AM. So just like any other AM process, we would have an energy source, which in this case is usually a source of UV light. It may be a laser, that is, it may have one point, or it may also be a UV floodlight. So that is, is projected over a large area instead of just a single point at a time. And in the raw material, that is in the resin, we have some photoinitiator particles, which are denoted by black dots, and the monomer. So as the name suggests, it is a monomer, and it will polymerize and form chain between other monomers to finally form the polymer, which is actually the final form of the 3D printed product. When it is irradiated by energy, so here we see H nu. This is from the famous Planck relation, where energy may be expressed as H nu. H is the Planck constant. So it has a value of 6.626 into the power minus 34 joule second. Nu is the frequency. So when the surface is irradiated by energy of a particular frequency, what happens is the photoinitiator particles get excited, and it leads to the generation of certain free radicals. In the diagram, this is represented by these small red dots. So these particles are now activated and they carry excess energy. And what happens is that they initiate the chain formation by passing on these radicals to the monomers, as we see here. So we have the start of certain chains, and this process progresses spontaneously in the form of a chain reaction. So say this passes on to this, again the radical may pass on to here, and so on, maybe to here, this again passes to here, and we have a polymeric chain. As the chain propagates, the polymer gets longer and longer, and finally the chain terminates when there are no more free radicals to pass around, and thus here we have complete chains. Say this is a complete polymer chain. This is how the object is manufactured, by repeating the process for each layer, and the uncured liquid is drained from the vat, and the object proceeds for further processing. Again, the time taken for this chain formation depends on the resin we are using, as well as the power wattage of our UV source, the layer thickness, and certain other process parameters. For a liquid photopolymerization based liquid AM process, there are certain subsystems which actually govern the working principle or the type of process. First among them is the photopolymer liquid itself. Second is the UV light. Third is the scanning system. We will discuss these in detail in the upcoming slides. The build direction and the recoating system. So among these, the scanning system can be galvanometer based. A galvanometer consists of a pair of mirrors which can be deflected. So while they remain stationary, I mean they remain hinged at a point, they can be suitably deflected or rotated. And this rotation or deflection deflects the energy beam. And thus the beam scans the area of interest. As Professor Kapil pointed out in his lecture, the galvanometer mirrors have very little inertia. And owing to this low inertia, they can be deflected very quickly. And because of the quick and fast movements of the galvanometer mirrors, the area can also be scanned very quickly. However, one drawback that might be apparent to some of you is that the cross section of a beam, say I have a beam of light falling on a surface, and here the cross section is circular, and this is, say, the position of my aperture. But when I deflect this beam of light to, say, another region which is far away from the optical axis. Say this is profile 2 and this is profile 1. How similar will these two profiles be? Or will there be a change? This is an important consideration. Second, the scanning system may utilize a flying liquid. So this is where, say, you have a set of nozzles in material jetting, and these nozzles actually dispense the resin on your build surface, and the build plate is stationary, whereas the deposition head itself moves in along the xy direction. Of course, this is also accompanied by a curing mechanism. So, say behind this or to the side, there is another mechanism to actually cure the deposited resin material almost simultaneously. And as the liquid itself is moving, it is referred to as a flying liquid method. They may be there may be flying optics based methods where, say in this case, the galvanometer mirrors were hinged to a point, so, but mostly fixed in space. Of course, they were deflecting or rotating about that point, but their position was fixed. In flying optics, the optical system itself may travel. So, say you have a system, this is a build plate, and you have a system of projecting light on the build plate, and your light system itself is moving along the xy direction in the xy plane while this is stationary. Because of the movement of the light source itself or the energy source itself, this such systems are referred to as flying optics. DLP stands for digital light processing. It is a trademarked name, I think trademarked by Texas Instruments, where we actually have an array of mirrors, as Professor Kapil demonstrated in his lecture. So you have many square mirrors in a rectangular array. And normally these would all be, their normals would all be parallel to the normal of the plane. So they would all be lying flat on the surface and pointing upwards. Now, depending on which areas of a particular slice you want to expose or you want to cure, you can suitably deflect these mirrors or you can suitably actuate these mirrors to shine your energy or to project your light on those specific regions only. So, by utilizing electromagnetic coils, these each individual mirror can be actuated. And again, the resolution of your final print will depend on the pixel size. Pixel size in this case will actually corroborate or be commensurate to the size of your each individual mirror in this mirror array, and it can give you very accurate prints. A mask-based scanning system, as we discussed, utilizes a negative of the region to be exposed and a floodlight-based illumination source, and can give you very fast scans. The shape of UV light itself may vary, and depending on your application, you may use a laser beam. So something which is very coherent and has a very small area. Say this beam spot diameter can be 6 micron or of similar order. Or you can use a floodlight where you are actually exposing your entire build area to light. So the entire area is exposed, and irrespective of which areas you want to keep or which areas you want to remove. And the areas of interest are actually marked out by the mask based or the digital light processing based techniques that we discussed in the last slide. Further classification of the subsystems may be based on the shape of the liquid. So first is VAT. So as the name suggests, in VAT photopolymerization, you have a vat or a container full of the liquid, and your printing takes place inside this vat. So maybe you have a build plate here, which in this certain example moves in the downward direction, so that printing always takes place in the plus Z direction. And your entire system is within this vat. Say I'm printing a pyramid. So my printed part is always inside. And here, the gap between the last deposited layer and the vat surface would nominally be equal to the layer height. Whereas in the case of a liquid jet, as we discussed, the liquid is dispensed for these discrete nozzles in the form of jets. So of course these nozzles might be placed very close together such that what we end up obtaining is actually a curtain of liquid, and it is simultaneously accompanied by a curing mechanism which is parallelly curing the deposited material. And this deposition head will travel in the x and y directions. In this case, the vat remains static in certain cases, or in other cases, it may also move where the liquid itself is flying. Another classification is based on the build direction. So, as we discussed, the build may progress in the z direction. For the build to progress in the z direction, the stage or the build platform should move in the negative z direction. And in each pass or in each step, the stage moves in negative z by the layer height h. In the case of a build along the negative z direction, say again, we have a VAT photopolymerization case, and this time I'm actually pulling the stage upwards. So the stage travels in the plus z direction so that my build is occurring along the negative z. And stage will move along the plus z direction by h in each step. What advantage will a negative z direction build offer over a part build in the positive z direction? So, especially in the case of liquid based AM processors, say this vat is full of liquid. And I think we have touched upon this point in the previous session also, that if this build were to have a hollow section, say this part is hollow, If I build it along a positive z direction, there will be accumulation of liquid in this hollow section. And say if it were to be covered in the next step, so this liquid will become entrapped. However, in this case, where the build is actually progressing along the negative z direction, there is no entrapment. The liquid flows out of the hollow cavity by the force of gravity itself. So we do not have to perform any additional step, and it does not get entrapped. This is one of the many advantages of building along the negative z direction. And another demonstrated direction is actually variable. So depending on your requirement, you do not have a fixed direction at all. In this case, the deposition head itself becomes flexible. So say you have an optic fiber that is delivering a laser attached to a suitable head, and this is flexible, and I can dip it in my vat, and depending on how I want the final printed part to be, I can move my deposition head freely such that it is always, you know, normal to whatever I am printing. And based on the movement of this flexible head, the final part I realize may be freeform. Recoating is another consideration, and such processes may have been classified on the basis of the recoating system. Recoating is where I am actually delivering. So in liquid-based AM processes, say I have built these couple of layers on top of a build plate or a substrate. And now when I want to print this next layer, what I have to do is I have to coat this top layer with a layer of the liquid resin. And then this liquid resin will be exposed or cured by the energy source, say by a laser in this case. And again, it'll form the next layer. But how do I coat this top layer with this new layer of resin? So there are three broad ways. One is deep dipping, where say this is the height of resin that we have. In the previous step, my part was already built to this height. Now I will dip this further to bring a layer of resin on top. So this much resin is now extra or coated, and again it will go somewhat further up and be exactly the layer height away edge. And I will have a recoater blade or a doctor's blade to actually take away or remove the excess resin. Thus, in each step, I will be only left with a layer of resin which is exactly unequal to height to the step size or the layer height. This is deep dipping because we are dipping the built layers deep into the liquid vat. In top feeding, we have a set of nozzles deliver a curtain of the liquid material. So when they are operating simultaneously, what you obtain is a curtain of liquid material, and this is deposited on top of my pre-built layers. As the feeding of the liquid is happening from the top direction, this is called top feeding. And in bottom feeding, of course, this is especially used when we are printing along the negative z direction. The feeding of the fresh resin is actually happening from the bottom. So if this is my vat and I will be moving my build plate along the positive z direction, then I move it by exactly the height, which is actually the layer height, to coat the last printed surface with a layer of resin to be utilized for the next step. This may be achieved by several means. It might be simply travel up along the z direction, or it might slide in the xy plane to obtain a new layer of resin. And what you will appreciate in this case is that, so here I needed a good volume of resin. Say I define it by the column of resin that I have, the height. A good or excess volume of resin was required in the case of deep dipping. In the case of top feeding also, we see that we need a good amount. But in the case of bottom feeding especially, and compared to deep dipping, in each step, I just need the minimum quantity of resin, which is simply equal to the height of the resin column should simply be equal to the step size or the layer height itself. So I can actually work with a very low quantity of resin in the vat. Or maybe I can pump in each step a very low quantity of resin. So this is more economical and less wasteful. And depending on these subsystems and how they are connected, we end up with the different photopolymerization based liquid AM processes. So some examples are here. So if you were to talk about 3D systems stereolithography, the first vat photopolymerization process, it uses a galvanometer based scanning system, uses a laser beam as the energy source, uses a liquid vat, and the build progresses along the z direction. And for recoating, it uses deep dipping. So when you connect all these dots, you end up with 3D systems SLA. Similarly, for say microstereolithography, which is another liquid AM process, it utilizes flying liquid. So the nozzles travel in the XY plane and a laser beam as the illuminating source, along with a vat, and the build progresses in the negative Z direction and utilizing bottom feeding. So mostly for every case where we will have negative Z direction, the feeding will be from the bottom. Then the process we obtain is called microstereolithography. Similar for the other processes. And now we'll break for a couple of minutes. And in the second half, we'll discuss certain questions that will help you solve the assignments of this week. So let us join again at 8:15. So let us resume. Okay, so let us look at some quick videos. So this is actually a 3D printed basketball, which I think has been approved by the NBA for use in actual games. And here you see an actual basketball player dribbling the ball. So maybe this is an example of non-conformal slicing and a part printed using some space filling methods. And in the next slide, we have an example of direct writing. So as we said, if the deposition head or the energy source is flexible and can freely move around, there need not be a fixed build direction. So as we see in this case, it appears that the printing is occurring in free space without any support structures. I'll just play it again. So as you see, there are no support structures. There is no fixed build direction. And yet the structure, which is actually a combination of polymer and ceramic, is standing. So for anyone who is interested, this is actually called direct writing. And it is a very interesting chemistry of actually the ink in this case, or the build material, the feedstock, and how the control of chemistry of that feedstock actually enables the printing of such supportless structures. So you may look it up. Now we'll solve certain questions that are based on the topics that were covered in this week. So the first question actually asks us that there are rectangular and square contours of given dimensions, which are fabricated using the laminated object manufacturing process from a square sheet of dimension 10 cross 10. So we have the sheet, which is actually our feedstock, and we have two contours. One is a rectangular contour of area 8 cross 3. Another is a square contour of area 5 cross 5. And we are asked to calculate the ratio of area of the unwanted material. So remember, in the case of LOM, say this is my useful region, or the region which I want to retain, and the rest of it I will fill by a grid cutting algorithm. And this area will be eliminated. The question is actually asking us to calculate what will be the unwanted area in case where I have a rectangular contour, in case where I have a square contour. So for the rectangular case, I know that the area of, say, the desirable region is 8 cross 3 centimeters square, or 24 centimeters square, and the total area of the sheet is 10 cross 10, or 100 centimeters square. So the unwanted area is actually total minus useful area, which comes out to be 76. Similarly, when we are calculating for the square contour, first we find the area of the desirable region. So it has dimensions of 5 cos 5, which is 25 centimeters square. The total area of the sheet will remain unchanged since we are using the same feedstock. Thus, we can calculate the unwanted area in this case also, which is the total minus the desirable, 75 in this case. And if I were to denote this by unwanted area with a subscript square and this by unwanted area with a subscript rectangle, I need u square by u rectangle. So is 75 by 76. This is very close to one. Please give me a moment, I'll just calculate it. Or 0.9868. So this is the answer that we needed, or the ratio of the unwanted material in the case of square to the unwanted material in the case of the rectangle. The second question speaks about infill density and says that we have a cube of given dimensions and a cuboid of certain given dimensions. They have different infill densities. Say for the cube it is 40%, for the rectangle it is 60%. They're fabricated using the FDM process. We are supposed to calculate the ratio of volume of infill material used. So what does this infill density actually mean? Say you have a cross section or a contour. So as we discussed, it will be filled by certain strategies. Say you will have 2 or 3 perimeter contours, and then you will raster it depending on the angle with the x-axis. This may even progress along any axis. But you see that these are discrete paths, and usually based on the infill density, they will not overlap unless the density is 100%. So there is some area where I am depositing material. Say this is FDM, so filament based material. But in all of this remaining area, which I have highlighted in red, it is actually a void. And the ratio of this filled or the printed to the ratio of the unfilled is infill density. So as we discussed, the toolpath that you actually choose for the printing process will vary this infill density, or for a chosen toolpath, we can vary the infill density. This will be achieved by changing the overlap. Say in this case, there is no overlap. For another case, I might have partial overlap, or this overlap may also increase substantially. I can control the infill density. So again, let us first calculate it for the cube. I know the volume of the cube. is 20 cross 20 cross 20, 8,000 centimeter cube. However, this is the volume of the total cubic geometry. This is not the volume of the material which I have actually extruded and filled this with. It has a density of only 40%. So the actual volume which I have extruded or used for printing is actually 40% of this. The remaining 60% is void or pores. Sorry. Uh, yeah, 40% of 8,000, which is 3,200 centimeter cube. Similarly, I calculate this for the cuboid. So the total volume or the nominal volume of the cuboid, 5 into 10 into 20. This is 200 into 5 is 1,000 centimeter cube. And I know the density, again, it is not 100%. It is 60% for the cuboid. So the volume extruded to actually construct this cuboid is only 60% of the nominal volume, which is 600 centimeter cube. Finally, I am asked to find the ratio of this volume of infill material, V cube by V cuboid. V cube is 3,200 and V cube is 600. So this comes out to be 32 by 6, or if we simplify further, 16 by 3. Or please give me a minute, I'll calculate. 5.33. So this is the ratio, or this is the quantity that we're asked to find in the second question. Next, we have certain concept-based questions. So this question asks us, what will be the difference in toolpath strategy for exterior contours obtained from direct slicing in one case and from indirect slicing in the other case? So just to give a quick recap, direct slicing is when we are slicing from the exact 3D geometry or the exact CAD geometry without the use of any intermediate step. Excuse me. And thus, since the geometry in this case is exact, when we slice it, the contours we obtain in each slice are also exact, as we can see from the example of the circle here. So in the slicing of an exact sphere, we'll obtain exact circles in each contour. So this is called direct slicing. Whereas in indirect slicing, again, we start with a exact CAD geometry, but we have this intermediate step where we actually approximate that exact geometry by tessellation into an STL file. And we are well aware that this STL file is approximate. It gives us a good representation of the complex surface, but it is not exact. And thus, for a sphere, which was a perfect sphere in a CAD model, when it is tessellated into an STL file, it becomes approximate. And when we slice this approximate STL file, what we will obtain is polygons in each slice. See, by increasing the number of sides of the polygon, we may approach a circle, but still it will never be exact. And this is called indirect slicing. So now we can work our way backwards and see that in indirect slicing, the contours we obtain are polygons, whereas in the case of direct slicing, the contours we obtain are curves. So what will change in each case is that in the case of indirect slicing, I can simply find the intersection points and interpolate between them using lines or straight lines to obtain the contour. This is possible because I have these polygon shaped contours in each case or in each layer because polygons. Whereas in the case of direct slicing, where our final contour is actually made up of curves. Again, when I slice it, I find the intersection points of each slicing plane with my STL file. And again, I interpolate between these points. But in this case, I cannot use lines. So this interpolation cannot be linear. So I have to use some other interpolation, such as quadratic polynomial or any other polynomial based interpolation, for example. But it cannot be linear. So this is the primary difference between the toolpath strategy for exterior contours when we are proceeding via a direct slicing versus via an indirect slicing step. The fourth question asks us to find the odd one out in the context of area filling methods for toolpath planning. And the options we have are laminated object manufacturing, stereolithography, binder jetting, and DD. Now, if it were based on the type of raw feedstock, we could have easily ruled out some of the others, but the context has been specified as well. So the context has to be area filling only. So for DD, we use a zigzag or a raster scan. For binder jetting also, this may be used, or even if some other step is used. What the odd one out is laminated object manufacturing, because in each of these cases, for binder jetting or for stereolithography, we concentrate on the region of interest or the desirable region, which is actually constituting our print. And in each layer, I'm focusing only on the region which is actually my part. I am less bothered about this surrounding region of the build plate. And so I concentrate my toolpath planning efforts on filling this contour only. How my toolpath will travel within this contour, or how it will deposit the perimeters and such other steps. Whereas in the case of laminated object manufacturing, I actually concentrate my efforts on generating the grid in this unwanted region. by a process called grid cutting. And rather I leave my desirable region untouched. So I will concentrate my efforts on generation of this Cartesian grid. Later I'll remove this unwanted material by any means, such as by using a laser, or if your sheets are made of paper or some soft material, by using a knife. And thus, laminated object manufacturing is the odd one out in this case, because we are concentrating our toolpath planning efforts on the unwanted region rather than the wanted regions, which is the case with the other processes. Question 5 asks us to determine that on the basis of sensitivity to UV energy source, what is the type of photopolymer material generally used in liquid AM processes? Is it a positive photoresist or is it a negative photoresist? So we may have studied this in a course that discussed optical lithography, but for a quick recap, so there are two sorts of photosensitive materials or photoresists. One is called a positive photoresist, the other is called a negative. And the difference is that in the case of photoresist, positive photoresist, say this is my mask and this is the layer of photoresist which I have applied on top of the substrate. And using this mask, I am selectively exposing certain areas which are grayed out, and I'm also highlighting by this black ink. And depending on the type of resist, whether it is positive or negative, either this exposed area will get washed out, like here, you cannot find the exposed area, and the area that were not exposed to light, that were prevented by the mask, survive after the chemical etching process. Or if the photoresist is negative, this exposed area or the cured area will actually survive. Now, from our discussion and from the lecture this week, we remember that usually what happens is in each layer of a liquid based AM process, the area that is exposed to light, or the area over which our light beam scans, actually survives. And the rest of the liquid is washed away, or it is taken away in the next step, or drained. Or in the laminated object manufacturing, uh, it is cut away. But concentrating on the liquid processes, so it is only the exposed regions which survive. And from the classification of negative and positive photoresists, we see that this corresponds to the case of the negative photoresist. So it may be said that generally the type of photosensitive resin used in liquid-based AM processes is of the negative type. In question 6, it says, during deposition of material in a single layer, there are certain steps at which the process becomes unstable. So certain steps that are commonly encountered in the deposition of each layer are listed here. And as we discussed in the lecture, at times the process becomes unstable because of excess deposition of material than the programmed extrusion rate, or because of less deposition. And we are asked to determine which of the following can be categorized as such unstable steps. So let us examine each of them one by one. Start of print. As we discussed, the deposition process is governed by inertia. And at the very start of print, it is often encountered that the volume of deposition is lower than programmed. So the start of print may be considered an unstable step. Turning a corner in a toolpath. Now, from basic mechanics, we know that the velocity of the deposition head when it turns a corner changes because of the change in direction, even if the constant speed is kept constant. Or even both may change, even the speed may change. To turn this corner, the deposition head will be subjected to certain forces, which will again invoke the inertia. And ideally, it will have to slow down while it approaches the turn. And after turning, it will move away quickly. So during this change in the travel speed of the deposition head, again, it is often found that more material is deposited at the corners. So usually with time, if say this is your, I mean, a nominally cubic geometry or a cuboidal geometry, what we will find is that with time, these corners are getting bulged up. And it might also look like in the center there is a dip. Thus, turning a corner in the toolpath may also be categorized as an unstable step. Similar to start of print, the stop of print also is governed by inertia and leads to less or more deposition than the programmed value. Change in z height of the deposition head or build platform. Now, during the change in the z height, usually there is no deposition. So the deposition head will deposit material in a single layer. And then when the z height changes, even either by movement of the build plate or by movement of the deposition head itself, no material is deposited. And so it cannot be called as an unstable step. Thus, A, B, and C are the correct options. Question 7 is discussing the advantages of bottom feeding method in vat photopolymerization. So we discussed this method at length. Let us look at the options. Less resin is required. Yes, this is true. As we discussed, since the build direction is actually along the negative z direction in this case, say I have certain pre-built layers. For this next layer, I mean, ideally, the height of resin column that I need can be equal to the height of the layer height only. I do not need excess resin in this case. So I may only pump in this required amount of resin, or the vat can have only this little amount of resin compared to a top feeding approach where the vat is usually filled to allow for deep dipping. Better accuracy and finish. So the accuracy will be determined by the optics and the resolution of the optics in terms of pixels. The finish will be determined by the layer height. And as we know, the layer thickness or layer height is governed by the movement of the Z stage in this case. It can be the same in both top feeding and bottom feeding. So this is not generally true or not necessarily true. And less chances of entrapment of uncured resin. Again, as we discussed, because of the inverted geometry, should our part have a hollow region, as the entire thing is inverted, there will be no entrapment of liquid in this hollow region, and it will flow out under the effect of gravity. Thus, even if in the subsequent step, the next layer were to actually cover this hollow section, there is very little chance of entrapment. Hence, this option is also correct, and we have options A and C in this case. These are the two advantages that bottom feeding approach offers over the top feeding in photopolymerization. The next question, and this was discussed by Professor Kapil in his lecture, is How can existing CAM packages be used for area filling of a freeform 3D surface? So we spoke about the area filling of 2D surfaces at great length, but we did not really discuss the 3D freeform surfaces because they are up and coming topics and still under active research. And people have tried various approaches, but there is no single unified or single most effective approach that has been used. One of the strategies which utilizes existing software or existing infrastructure to actually to achieve this is by the use of existing CAM packages. And as Professor Kapil discussed, this can be done in the way that from the existing CAM package, we extract the machining or finishing strategy of the outermost contour. Once we know this strategy, we obtain the G code, modify it if necessary. Of course, the modifications could only be minor. And using this G code, instead of removing the material, which would have been done by the CAM program or the CAM algorithm, removal of material, which is a subtractive step, we utilize this G code, of course, with the necessary offset or the necessary changes to add material to the freeform surface. Thus, existing CAM packages can actually be leveraged to fill the areas in 3D. Question 9 asks us, how are the individual mirrors of a digital light processing system manipulated? So this illustration is from Professor Kapil's slides itself. On the left, we are seeing a digital light processing mirror array. We see that the mirrors are so fine that we cannot really see the boundaries between adjacent mirror. Of course, this is highly exaggerated. The size of mirrors is very small, and the boundaries between them are non-visible. In the enlarged view to the right, we see certain terminology related to this digital light processing. One is the micro mirror pitch, which is actually the distance between the centers of two adjacent mirrors, and the micro mirror size, which is the dimension of each mirror. So usually these mirrors will be square and they'll be arranged in a rectangular array. The size of each mirror is actually equal to the pixel size for the process or the resolution of the machine. And for each of these mirrors, here we see that there are a pair of mirrors. They are actuated, and usually when they are in the usually when they're not actuated, they will be lying normal to the surface, and by the use of electromagnetic coils, each of these individual mirrors can be suitably uh, moved or actuated to shine light on the platform. So say if for this nominal off state or nominal on state, it can vary depending on the process. Say in the on state of the mirror, when it is normal to the mirror array, all the light is getting reflected back almost along the same direction. So the incident and reflected rays are nearly coincident and it is not reaching the build platform. Whereas in the off state, when the mirror is actually deflected, the light that is incident on the mirror gets reflected onto the build platform. And this material on the build platform is exposed to the light and cured. So individual mirrors of a DLP system are manipulated by the use of electromagnetic coils. Question 10 is discussing the disadvantages of a galvanometer based liquid AM process. So, if we recall, the galvanometer based process uses a set of two mirrors. The mirrors are hinged or fixed in space, but they can be deflected or rotated to deflect the incident beam. And through the deflection of these beams, we can scan the entire region of interest with our laser based illumination source. Again, these mirrors have very little inertia and they are very light, and this enables us to deflect them very quickly. Thus, the scanning is also very fast. So, we are asked to discuss or point out the disadvantages of a galvanometer based liquid AM process. Is low scanning speed a disadvantage? No, we just discussed that because of the low inertia, the scanning speeds are actually very high. So, this is not a disadvantage. High production time. So, because of the raster scanning, even though the scan speed itself is pretty fast, but even then it is only scanning one point at a time. So, it is point by point, or I mean, essentially these are very small areas, but compared to a floodlight which illuminates the entire region in a single go, this may be approximated as points only. So compared to a point by point scan, even if the scan is very fast, an area scan will always be faster because it is illuminating the entire surface all at once. So it is almost instantaneous. This high production time or very long production time is definitely a disadvantage of galvanometer based AM processes. Low accuracy. Now, because of the very fine deflection of the laser beam source and the very small spot size, the accuracy can actually be pretty good when it comes to capturing the external contour, for example. This is not a disadvantage. Change in beam shape away from the optical axis. As we were discussing during the earlier half of this session, when a beam of laser is incident on my build platform, it will have a cross section. Say this is perfectly circular. When it is coincident to or very near to the optical axis or the center of the aperture. But when I'm deflecting the same beam to the edge of the surface using galvanometers, and because as we can see that along this curvature, the beam will have the same cross section. But my build plate is somewhere here if I'm looking at it from the side. So when this beam is actually reaching the plate, it becomes elliptical. Thus, there is stigmation error. Of the beam. When it is deflected to far regions, far away from the optical axis, the profile of the spot did not be circular as it was near the optical axis itself. So the change in beam shape away from the optical axis is a definite disadvantage. Thus, B and D are the correct options. So this is all I had for today's session. So if you have any doubts, please feel free to unmute and ask. And if there are no doubts, I will bring this session to a close. Thank you. I am Sourav Goswami from IIT Bombay, and we'll meet again next week. Happy Independence Day once again.